So in this video, we'll be looking at volume, constant volume calorimetry. And that is as opposed to constant pressure calorimetry, which we looked at in the last video, constant pressure calorimetry, where we looked at problems having to do with coffee cup calorimeters. And so in this video, looking at constant volume calorimetry, we will be actually using a different apparatus, and that is going to be a bomb calorimeter. A bomb calorimeter. So in case you haven't or you aren't familiar with constant pressure calorimetry, I recommend checking out my last video where we went over this. But in case we need a quick recap, I will just quickly go over and somewhat compare what we're looking at with constant pressure versus constant volume calorimetry. So to recap, our constant pressure calorimeters, or coffee cup calorimeters, is going to include is going to be composed of a coffee cup made of styrofoam, and that's because our styrofoam is a good thermal insulator, preventing the outflow of heat and inflow of heat. So we're going to then have this cup filled with some sort of aqueous solution. Let's say this is water, because we're trying to, look at the heat of dissolution of NaCl, for instance. And so then we will have our NaCl in this solution. And in order to measure the change in temperature that is associated with this reaction, we will also have a thermometer in here, and additionally there will also be a stirrer, and the stirrer again is just to allow for the equal distribution of our heat throughout the solution. And this entire thing will be sealed or covered in order to again prevent our heat from leaving or other heat from entering. And so when we're looking at these types of coffee cup calorimetry problems, we can tell that this heat of our reaction, this heat of the reaction at constant pressure, this QP, Q again meaning heat, and the subscript P is referring to the fact that this is occurring at constant pressure, is going to be equal to our change in enthalpy. So this is a very important thing to keep in mind, this relation that our constant pressure, at constant pressure, the heat that results from this reaction is going to be equal to our change in enthalpy. And that is something that is a distinction between our coffee cup calorimeter and our bomb calorimeter. And the reason is, I guess, will make sense when we look at the bomb calorimeter apparatus. So looking at that very thing, we can see that our bomb calorimeter is going to be composed of this rigid container. Our rigid container is going to be filled with water, and inside of this water we will also have what is called as a combustion chamber. And so inside of this combustion chamber will be what we are trying to combust, our chemical or compound of interest. Let's say it's going to be inside of this chamber, and so connecting to this chamber and to the compound that we are trying to combust will be these two ignition wires. And so these ignition wires will then ignite the sample, combusting it. And in order to then measure the change in temperature that the heat released by this combustion will produce, we will also again have a thermometer. And to allow for the equal distribution or even distribution, uniform distribution of this heat, will again be a stirrer. So this comparatively more complex apparatus is what a bomb calorimeter, entails. Slightly more complicated than that of a coffee cup calorimeter. But in any case, what is very important to understand, and it also is, why it is called constant volume calorimetry, is because this container is very rigid in that it will not expand or contract due to these changes in temperature. Our container, being made of a very rigid material, will retain its volume. And this makes sense when we're looking at the first law of thermodynamics. We know that the change in internal energy is going to be equal to the heat, that is Q, plus our work, which is W. And in this case, the combustion of this reaction, the energy produced by the combustion of our compound here, is not going to result in any work being done. This container is too rigid for any expansion of the container, so there will be no work. Our W in this case will be equal to 0. And so that means that our change in internal energy is simply going to be equal to Q. So all of the energy that will be released by combusting this sample using these ignition wires will be in the form of heat. None of it will be used to do any work. And so in this case, our delta E, our change in internal energy, is going to be equal to Q. And this is an important distinction. When we were looking at coffee cup calorimeters, when you're looking at coffee cup calorimeters, you can use your heat to find our change in enthalpy. But that again is because this only works when we're looking at constant pressure. Whereas with our constant volume calorimetry, there is not a constant pressure here. There will be a change in pressure, and because of that, we will not be able to find our change in enthalpy, but rather looking at our first law of thermodynamics, we will be able to find our change in internal energy. So if you're trying to find the change in internal energy, you're going to want to use a bomb calorimeter, whereas if you're trying to find the change in enthalpy, that's going to be a coffee cup calorimeter. So now, keeping these things in mind, let's look at a problem. So, looking at the problem at hand, we see that when 2.5 grams of acetylene is burned in a bomb calorimeter with a heat capacity of 10.85 kilojoules per degree Celsius, the temperature increases from 23.488 degrees Celsius to 34.988 degrees Celsius. What is the delta E? What is the change in internal energy in kilojoules per mole for this combustion reaction? So, in bomb calorimetry, as we were talking about, well, one, this is occurring at constant volume. We're trying to find our internal energy. We can't find the enthalpy, and that's what the problem is asking for. But we're told, again, here, we're given in the problem our heat capacity of the calorimeter. And so when we're looking at constant volume calorimetry, bomb calorimetry problems, we will be using this primary formula, which is going to be Q equals C delta T. And this C, again, is the C of the calorimeter, the heat capacity of our calorimeter, which is provided to us in our problem. And so we will begin the problem then by calculating this temperature change. So to figure out how much the temperature changed during the reaction, this delta T is going to be equal to our final temperature minus our initial temperature. And given in our problem, we do find our final and initial temperatures, and so this is simply going to be equal to 34.988 degrees Celsius minus 23.488 degrees Celsius, giving us a temperature change of 11.5 degrees Celsius. So this is going to be our delta T. So the temperature here increased by 11.5 degrees Celsius. So let's clear out some space here and just note that number off on the side. So we see that our delta T is going to be equal to 11.5 degrees Celsius. So now let's calculate the heat absorbed by the calorimeter. So we can find this heat absorbed by the entire calorimeter setup in a bomb calorimeter. We're going to use this formula, right? So this heat Q is going to be equal to our C cal, the heat capacity of our calorimeter, which we're told is 10.85 kilojoules per degree Celsius. And we found our delta T to be 11.5 degrees Celsius. And so we can cancel out these units of degrees Celsius, giving us our answer of 124.775 kilojoules. And so this is going to be our Q of our calorimeter. So the heat absorbed by the calorimeter is going to be 124.775 kilojoules. So now we need to relate this heat to the reaction, because remember, in bomb calorimetry, the heat that is gained by the calorimeter is going to be equal in magnitude but opposite in sign to the heat released by the reaction. So this heat relative to the calorimeter is a positive value because this heat is being absorbed by the calorimeter. But if we were to look at this heat relative to the reaction, Well, the reaction is releasing heat. It is losing heat. So this heat is going to have a negative value. So our heat of reaction is actually going to be negative our heat of our calorimeter. So now again, we can just clear up some of this room. Let's clear up this, keep our numbers in mind, and we can see that, well, if our heat of reaction is equal to the negative of our heat of our calorimeter, well, that is just going to be negative 124.775 kilojoules. Right, negative 124.775 kilojoules. This is going to be the heat of reaction, the heat that is released through the combustion of our acetylene, our 2.5 gram sample of acetylene to be specific. And so this negative sign is indicating that the reaction released heat, or in other words, it is an exothermic reaction. It is an exothermic reaction. It is one that releases heat into the environment. And well, now the last step is going to be calculating the moles of acetylene burned. Well, really not the last step technically, but close to the last step is going to be finding the moles of acetylene burned. And we're doing this because you can see that we're asked for our answer, our change in internal energy in units of kilojoules per mole of this combustion reaction. So we found that negative 124.775 kilojoules of heat was released as a result of this reaction by combusting 2.5 grams of acetylene. And so in order to get this answer in terms of moles, we're going to have to convert this 2.5 grams of acetylene into units of moles. How many moles of acetylene is 2.5 grams? And well, how can we go from grams to moles? Well, we simply have to use our molar mass to do so. And so we can begin by finding the molar mass of acetylene. So the molar mass of acetylene, which is C2H2, hopefully by now you are familiar with how to find the molar mass, so I won't really be explaining that. So our molar mass is just going to be 2 times 12.01 grams per mole plus 2 times 1.008 grams per mole. And this gives us a molar mass of 26.04 grams per mole. And so now we can then convert this 2.5 gram sample of acetylene by setting a stoichiometric relation in this way, by saying 2.5 grams of acetylene. We know that 1 mole of our acetylene is 26.04 grams. Canceling out our units of grams gives us an answer of 0.0960 moles of acetylene. All right, and now this is the last step. So now we calculate our change in internal energy in per mole. And so we see that we have 0.0960 moles of acetylene. And we've found that this 2.5 gram sample, or this 0.960 moles of acetylene, has produced negative 124.775 kilojoules of our heat. So, well, this delta E per mole of acetylene is going to simply be that heat of reaction, this value here, divided by the number of moles of acetylene that we found. And so this is just going to be negative 124.775 kilojoules divided by 0.0960 moles of acetylene. And so that is then just going to give us our answer. Our delta E is going to be approximately negative 1,300 kilojoules per mole. And this then is going to be our change in our change in internal energy for this combustion reaction. And so this large negative value just tells us that the combustion of acetylene is highly exothermic. It releases a lot of heat. And this also just makes sense because it will, in context, since acetylene is used as a high energy fuel in torches, with acetylene torches. And so it just makes sense that this reaction would be highly exothermic. And so now just some final recaps of our answers. Well, we see that the heat that is absorbed by the calorimeter, well, that is going to be positive 124.775. It's important that you keep everything clear, right? Like in your head as to what is going to be positive, what is going to be negative, what each value represents. And so our heat absorbed by the calorimeter, well, that is going to be 124.775 kilojoules. Our heat of reaction, well, that is just negative 124.775 kilojoules. And the energy change per mole of C2H2 is going to be negative 1300 kilojoules per mole. So again, we got this using pretty straightforward steps. We found our change in temperature, calculated our Q, which we found using Q equals C delta T. We found the number of moles of acetylene, and simply then divided to get our answer, our change in internal energy per mole. And so just to finally just recap, and some of the main takeaways here really is in bomb calorimetry, because this reaction is occurring at constant volume, this change in internal energy is going to correspond to the change, or the delta E, right, is going to correspond to the change in internal energy, not enthalpy. If you wanted to find your change in enthalpy, we would have to be using a coffee cup calorimeter, a reaction that's occurring at constant pressure, so that our heat at constant pressure is what we would be using to find that change in enthalpy. So main takeaways then, if you want to take one thing away looking at a problem, or just to keep in mind, if you want to find our change in enthalpy, use a coffee cup calorimeter. If you want to find your change in internal energy or combustion of reaction, right, that is going to be your bomb calorimeter. So hopefully you got some value out of this video and everything made some sense. If you did, please show your support by liking and subscribing, and leave in the comments what you'd like to see next. And I'll see you guys in the next one.